Hello everyone, welcome to Gate Pass. In this video I am going to take two more problems which came in Gate 2011 and that were related to thermodynamics. So let's see the first problem. It was question number 24. It says that you have two systems for compressing air to 10 bar. The first one, which is denoted by K1, it is a single stage compressor, and the second one is a multi-stage compressor denoted by K2. It has interstage cooling in between. Okay. Now they have said which statement is incorrect out of these four. Okay. Let's see. K2 will have knockout pots in between stages. We are providing interstage cooling. That means there are some heat exchangers which take out heat after compression. Okay. And we all know that knockout pots are provided after your heat exchangers in order to remove any gases which have condensed. Okay, so K2 will have knockout pots after your heat exchangers. So this statement is correct. Discharge temperature of K1 is greater than K2. Of course, since we are not providing any cooling in case of K1, so the discharge temperature of K1 will be higher. K2 will consume more power than K1. To understand this statement, let's go on the PV plot. Okay, and let's assume that both these compressors, single stage and multi-stage, they have their suction pressures as P1 and their discharge pressure is P2. Okay, so let's say for K1, this is my suction pressure. After this, the compression takes place, okay, up to this point, and then there is discharge. So the work which is required for this compression, it will be area under this curve. Okay. Now let's see the case of multi-stage compressor. Here let's say that first compressor has taken in air. Now it is compressing up to some point. When the compression has reached, let's say, to the intermediate stage, then we provide cooling, okay, at constant pressure, and then after cooling we send it to second stage for further compression to P2. Let's say again this is some polytropic compression. Okay, so then the work required will be the area in this under this curve. Okay, so the amount of work which you have saved for same compression is this much. Okay, so that's what we see for single stage compressor. We require more power than the multi-stage compressor. So in this case your option C is wrong, which says that K2 will consume more power. We have seen over here that K2 will consume less power than K1. So this statement is wrong. Let's see quickly the remaining statement. Cost of K2 will be more than K1. Of course, K2, it is a multi-stage compressor. Okay, so you have more than one unit first of all. Then you have interstage cooling, so you have to provide heat exchangers and knockout pots in between. So that will increase the cost of your K2. So this statement is also correct. Out of these four statements, your option C is wrong. Now let's move on to the next problem. So the next problem which I am going to take is question number 33. It talks about a binary mixture of methyl-ethyl ketone, which is marked as component 1, and toluene as component 2. Okay, and they have given you certain information, that is your ln gamma 1, that is gamma 1 and gamma 2, these are activity coefficients. They give you the non-ideal behavior of the liquid phase. Okay, so your ln gamma 1 and ln gamma 2, they are given as a function of mole fractions, and psi 1 and psi 2, which are composition independent parameters, but their values are not given. Okay, further they have given you the value of ln gamma 1 at infinite dilution. When I say infinite dilution, it means that your x1 tends to 0. Similarly, they have given you the value of ln gamma 2 at infinite dilution, that is when your x2 tends to 0. Okay, they have also provided you the saturation pressures of component 1 and 2 at temperature 323 Kelvin. Now they have said that assume that your vapor phase is ideal and calculate your equilibrium pressure when your mole fraction of component 2 in the liquid phase is 0.9. Okay, so once again this is a problem of vapor liquid equilibrium. So what we are going to use? We are going to use our Raoult's law. So I am going to write my Raoult's law for both the components. Okay, so y1p that is equal to x1 gamma 1 P1 saturation. So I'm assuming that my vapor phase is ideal, so that's why you do not have a fugacity coefficient over here, but your liquid phase is non-ideal, so that's why I have included my activity coefficient on this side. Okay. Similarly, for component 2, I am going to write x2 gamma 2 P2 saturation. Now how do you find your equilibrium pressure? You add these two, y1p plus y2p, p comes out common, y1 plus y2 is 1, so I'm going to directly write P, that is equal to x1 gamma 1 P1 saturation plus x2 gamma 2 P2 saturation. Okay, so in this equation what you will see is that we have to find our equilibrium pressure P. We know x1 and x2, we know P1 saturation and P2 saturation. What we don't know is gamma 1 and gamma 2. Okay, so that we are going to find out next. We are going to use these equations and the values of ln gamma 1 and ln gamma 2 at infinite dilution. So let's do that. So ln gamma 1 at infinite dilution, okay, that is equal to, let's put x1 equal to 0, so that means x2 is 1. So this term will be 1 and this term will become 0, and what I am left with is only psi 1 minus psi 2, and that is equal to 0.4. Similarly, for ln gamma 2 infinity, that is ln gamma 2 at infinite dilution, your x2 tends to 0 in this equation and x1 tends to 1. So this term goes to 0, this is 1, so I am left with only psi 1 plus psi 2, that is equal to 0.2. Now you have two equations and two unknowns. Quickly go and solve these for psi 1 and psi 2, and you will find that your psi 1 is equal to 0.3 and your psi 2 is equal to minus 0.1. Okay. Once we have calculated our psi 1 and psi 2 values, rest all is very simple. For given condition, that is for your x2 is equal to 0.9 and x1 equal to 0.1, we are going to calculate the values of gamma 1 and gamma 2 to be used in this equation. Okay, so let's write ln gamma 1, that is equal to x2 0.9 square, psi 1 is 0.3 minus psi 2, psi 2 is minus 0.1, okay, plus 4 times psi 2 times x1, which is 0.1. Okay, so this is your equation. Just go ahead and solve it for gamma 1 and you will get the value of gamma 1 as 1.338. Similarly, put the values of x1, x2, psi 1 and psi 2 in this, and from that calculate your gamma 2 value, and the gamma 2 value, it comes out to be 1.0056. Now what you have to do is put these values in this equation and find out the equilibrium pressure. If you do that, you get pressure that is equal to x1. What is x1? 0.1 times gamma 1, 1.338 times P1 saturation, that is 36.9, plus x2, that is 0.9, multiply it with gamma 2, that is 1.0056, multiply it with P2 saturation, that is 12.3 kilopascals. So do these calculations and you will find the equilibrium pressure. My answer comes out to be 16.06 kilopascals, or round it off and say 16 kilopascal. Okay, so you have been provided with 4 options, and this was option number C, 16 kilopascal, which was correct. Okay, so what you observe is that after every year or two you have certain problem which is about vapor liquid equilibrium, and you have to use either Raoult's law or Henry's law to solve it. Okay, these are very simple problems and but very important at the same time. So I hope you liked my teaching, and if you like this video, please don't forget to subscribe to my channel, and thanks for watching.